Hello, this is Dr. James Camp at Lee College in Baytown, Texas, and this is my introduction to potentials as part of our unit on neurophysiology. Okay, so what's a potential? You may or may not have learned at some point in your schooling the idea of kinetic energy. Kinetic energy is energy you can see happening, like the energy of an object in motion or the energy of a light bulb glowing, or sometimes you can't see it, but you can hear it, like the humming of your car engine when it's running. The opposite of kinetic energy is potential energy. Potential energy is energy that is stored. Okay, so when a person climbs up on a diving board, stands there waiting to dive, they have just stored a great amount of energy in their body by climbing up to that high place. But that energy isn't doing anything right now. It's potential energy. As soon as they jump off the diving board, they fall very quickly into the water, and that becomes kinetic energy all of a sudden. You can see them moving. So potential energy and kinetic energy are related. You store up potential energy and then you use it to make kinetic energy. Other examples of potential energy: the gasoline in your car's tank has the potential to make make your car start humming and your engine start humming and your car start going. We call that chemical potential energy. A battery on the shelf or in a box has the potential to power an electrical device, but it's not until you plug the battery into that device or turn the device on that you see kinetic electrical energy happening. So we call that electrical potential. In this class, in biology class, when we talk about potential, we're always talking about electrical potential. So what is an electrical potential? Okay, electrical charges that are moving have, no surprise, kinetic energy. So if we have a battery plugged into a light bulb and that light bulb is glowing, that's kinetic energy. Electrical charges that are not moving but want to move have potential energy. So a battery that is just sitting here without the light bulb connected to it is full of potential energy, unless it's a dead battery. So what makes those electrical charges want to move? Well, electrical charges, like most things in life, are attracted to their opposites. So if I have a positive charge over here and a negative charge over here, the positive charge is attracted to the negative charge is attracted to the positive. They would want to move to come together, and either of those movements, whether it's the positive charge moving or the negative charge moving, creates an electrical current, which is that kinetic energy. And as those electrical charges move, they can make work happen. They can make a motor turn or a light bulb glow or a cell phone do its thing, all of that. Now, what if I put an insulator here between these? The positive charges would build up on one side of the insulator. The negative charges would build up on the other side of the insulator. We'd have a little gap. And across that gap, we would measure, let's see, we're using colors badly here, so I'm going to make potential energy blue again, like I did on the last slide. Okay, so we've got electrical potential energy, or just electrical potential, which is measured in volts. Okay, so if you've ever looked at a battery and it said it's a 12-volt battery or a 9-volt battery, what they're talking about is it's going to produce positive charges, lots of positive charges on one end and lots of negative charges on the other end, and the amount of potential energy that it's put into separating those charges so that they want to flow back around a wire, okay, is 12 volts or 9 volts or something like that. Of how much a system of electrical charges wants to move, sorry, is called the electrical potential. There I go again. Of the system, and it is measured in units called volts. Okay, so what does this have to do with the cell? Well, all cells in the body have a membrane potential. So again, if we define an electrical potential, sometimes called a voltage, this is one of the few measurements in science where we use the unit sometimes to describe the thing. We would never say that the distance you walked today was your meterage, or that the amount of fluid you drank was your literage. But we would say that your potential is your voltage, and I'm not sure why, but that has come to be common language. So your electrical potential, as you can see here, is if we took, it's a measurement of how these charges, so we've got, once again, negative charges on the inside of this membrane, positive charges on the outside of this membrane, and the separation, the charge separation in the system is our electrical potential. Okay, so in a neuron, or a muscle fiber for that matter, at rest, when there's no electricity moving, it turns out that there are more negative charges inside the cell and more positive charges outside the cell. The reason for this is that we have a lot of negatively charged proteins inside the cell that are busy doing cell work. Okay, that's what proteins do. They do the work of the cell. And we have a lot of sodium ions that are pumped outside the cell that contain positive charges and hang out there near the cell membrane, forming a membrane potential. This is maintained by a sodium potassium pump that moves 3 sodium. Sorry, that was an awful bit of drawing here. Awful bit of writing. Sodium. Moves 3 sodium out of the cell and 2 potassium into the cell at a time. Now you can imagine if you're pushing 3 positives out and only 2 positives in, you're going to end up with more positives outside and more negatives inside. For this reason, okay, we say that the resting membrane potential is negative. Okay, we want to look at the potential inside the cell compared to the outside of the cell. There are more negative charges inside the cell, so the potential is negative. If we had a tiny voltmeter that fit inside the neuron, like that, okay, and we actually do. There are such things. They're called micro electrodes that we can stick inside a cell and measure the the membrane potential, it would read negative 70 millivolts at rest. So there are four magic numbers I want you to memorize today, or three magic numbers I want you to memorize today. The first is resting membrane potential, and that is always in a neuron going to be minus 70 millivolts. Okay, so what does this have to do with nerve signal potentials? Resting membrane potential is, as we said, minus 70 millivolts. So if we have a graph of our potential, minus 70 is down here. Okay. The neuron will fire a signal down its axon when a threshold potential of minus 55 millivolts is reached. So minus 55. Some of you may be of an age old enough to remember that DeLoreans can time travel at 88 miles per hour. That's an example of a threshold. You have to get to a certain value for something to happen. Well, the threshold for neurons is minus 55 millivolts. Okay. Graded potentials change this resting potential slightly. Changes can be positive, which we call excitatory, because we're exciting the cell towards threshold, or the changes can be negative, which we call inhibitory, because you're moving the cell back away from threshold, so you're inhibiting any further neural signals. Changes tend to be 5 to 10 millivolts at a time, depending on the nature of the upstream signal, which is called a stimulus. The stimulus may be a signal from another nerve, another neuron. For interneurons or muscle neurons, it always is. If you're a sensory neuron, the stimulus might be another neuron, or it might be a sensory receptor, like a photoreceptor in the eyes, or a hair cell in the ears, or a corpuscle in the skin. Changes for these graded potentials are short-lived, and they fade as they travel. Okay, so if it starts out as a plus 10 millivolt, by the time it reaches the other end of the cell body, the soma, it might be a plus 8 millivolt signal at that point. And the membrane remains what we call polarized. That means it retains its negative polarity. So you may get up a little bit or down a little bit, but you're still negative. However, changes do sum up at the axon hillock, so that if you got several positive signals in a row, you would eventually hit this threshold. The opposite of a graded potential is an action potential. Action potentials happen when you hit threshold, and they shoot up to plus 30 millivolts. Okay, they are all or nothing. They always go up to plus 30 millivolts, or they just don't happen. And we refer to that, because it is now a positive cell membrane potential, as depolarized. This change is also short-lived. Okay, in fact, it immediately reverses course and shoots back down, but not before it has passed its signal on to the next part of the cell membrane. Remember that propagation that we talked about. And as it passes, as it propagates, it does not fade, okay? So it will remain plus 30 all the way down the cell. You'll have, if you have a cell membrane here, you'll jump to plus 30 here, then you'll jump to plus 30 here, and you'll propagate, then you'll jump to plus 30 here, and it'll just keep propagating like that all the way down the cell membrane until it reaches the terminal of the axon. Okay, so those are your three types of potentials: resting, graded, and action potentials, and also your threshold potential. That is what signals the change from a graded potential to an action potential. In the next lecture, we'll talk about how all of these things come together to make a nerve signal travel across a cell. Happy studying, and I'll see you in the next video.